Evaluate the double integral of e to the 2x plus y dA over the region R, where R is the set of points where x ranges between -1 and +1, and y ranges between -2 and 0. In this particular problem, we're given an image of what this might look like conceptually, but if you note the range of values on the x and the y, this isn't exactly the region that we're integrating over. And that's actually stated in this problem that the image might be slightly different than what you're actually working. And that's fine. What we need to know and what's important here is the definition of what our region R is in the plane, and that's certainly given right here. And setting up this double integral is actually fairly straightforward because this region would be rectangular. So the integral that we're going to work through would be the double integral of e to the 2x plus y. And then instead of dA, we're going to change that into either dy dx or dx dy. And it doesn't really matter which we choose here because this is a rectangular region that we're integrating over, but I tend to go with dy dx unless I have a good reason to go the other way around. Now, the bounds of integrals, if we start inward here, we have dy, so the innermost integral is the bounds on y, and y ranges from -2 to 0, and x, those bounds there are -1 and +1. So now that we have our integral set up, it's a matter of evaluating. And there really are more than a couple of ways of evaluating this particular integral. I'll try and do it the cleanest way that I know how. So first thing is one property that we have of exponential functions is that whenever you have an exponential function with an exponent that has two things added, you can split that up into two separate exponential functions with the same base that are multiplied. And if we do that, then e to the 2x is not dependent upon the variable y. So you can actually split this up into -1 to 1, e to the 2x, and just pulling that out of the integral, and then e to the y on the inside of my dy integral, and have this. Now, more than that, oh, I need my bounds of integral here, obviously. But more than that, there's a theorem that allows us that if we have two functions that are separable from one another, so that we don't have any y variables mixed with x variables or anything of that nature, you can actually split this up into two separate integrals. So e to the 2x dx times the integral from -2 to 0 e to the y dy. And what that allows you to do is to take these integrals at the same time and arrive at an answer a bit faster than if you had done the innermost integral first with respect to y, gotten that answer, and then done the outermost integral with respect to x and gotten that answer. You'll end up with the same final result because these functions are completely separable by variable. So let's work this through. So starting with the first integral, integrating e to the 2x with respect to x, you might need to go off to the side and do that integral with u substitution. And if you need to, that's perfectly fine. So for instance, e to the 2x dx, if I let u be that exponent, then du is 2 dx, or dx is equal to 1/2 of du. Oops. There we go. So this becomes 1/2 of the integral of e to the u du, and since e to the u is its own integral, this becomes e to the u on its own. I'm not going to worry about the plus c because I'm plugging this back into a definite integral, so the plus c isn't going to make any difference. And then that goes back into e to the 2x. All right, if you also want to speed things up, Just know that if your integral is only off by a constant multiplier, then just integrate the function as you would normally, the outer function, and divide by that constant. So anyhow, we should end up with 1 half e to the 2x, and we need to evaluate that from -1 to +1, and then we're going to multiply that by e to the y is its own integral with respect to y, so just e to the y evaluated from -2 to 0. So this will be 1 half e to the 2x evaluated at 1 would just be 2, minus e to the 2x evaluated at -1 would be -2. E to the y evaluated at 0, that's going to be e to the 0. And we know something raised to the 0th power is just 1. So I'll go ahead and make that 1. Then minus e to the y evaluated at -2 would be e to the -2. And there's our answer. And if you need an approximation, you can put that in your calculator and come up with an approximation. But this is a perfectly valid exact answer.